Okay, so having done all of that, let's just do one example of a higher order system, okay? So just how do we incorporate now maybe a 3 by 3 system? So we're going to solve y prime equals a times y, where we're given this matrix, and we're going to find the eigenvalues and eigenvectors, and then from there, we're going to find the solution. So we're going to take the determinant of a minus lambda times I. So that's the determinant of the matrix, 1 minus lambda, 1, 1, 0, 1 minus lambda, negative 1, and then 0, 1, and 1 minus lambda. So if we expand around the first column, then this becomes 1 minus lambda times the determinant of the smaller matrix, 1 minus lambda, negative 1, 1, 1 minus lambda. And so this actually becomes 1 minus lambda times 1 minus lambda squared plus 1. Another way that we can write that is 1 minus lambda times, if I expand that out, I get lambda squared minus 2 lambda plus 1, so that gives me plus 2. And so lambda is equal to 1, or we can use the quadratic formula and we get 2 plus or minus the square root of 4 minus 4 times 2 over 2. That's also known as 1 plus or minus I if we simplify. Okay, so what I have is 1 real eigenvalue and 2 complex eigenvalues. So I can let lambda equal 1, and I can try to solve this system. A minus I times v is equal to 0. So I'm going to take the matrix where I subtract off lambda times I. That matrix is going to be 0, 1, 1. The right-hand side of this problem is going to be 0. Then I'm going to get 0. And when I subtract off 1, I'm going to get 0 and negative 1. And then I'm going to get 0, 0, 1, 0. Okay, so this is the matrix that I have to work with, and I want to row reduce that matrix. So I'm going to have 0, 1, 1. I'm going to multiply the second row by 1 so that I'm going to get negative 1. So I get 0, 0, 1. And then when I subtract row 3 from row 1, I'm going to get 0, 0, and negative 1. Okay, so then my last step of the row reduction is that I can add the second and third rows together, replace the third row. So I'm going to get all zeros on the bottom, which I definitely wanted to occur, that I get all zeros on the bottom there, to make sure that I had one free variable. Okay, and so I'm just going to look at this system rather simply. I'm going to actually, in fact, I'm going to look at what I can do with the first row, I could take the first row and subtract off the second row. And so then I would get 0, 1, 0 there. Okay, and then that tells me that I have one free variable. Okay, and so my eigenvector is going to, V1 is going to be a 1 where the free variable is. And then the first row tells me that the second component must be 0. And then the third row tells me that the third component must be 0. So my eigenvector is in fact going to be 1, 0, 0. Okay, I'm going to just clean this up for a second so that I have room. Just want to have some room for my eigenvector. Okay. Now, let's move on to our second eigenvalue. That's going to be 1 plus I. Okay. So looking at 1 plus I, I'm going to plug that into my matrix. So I actually need that matrix over there. So when I take 1 and then subtract 1 plus I, I'm going to get a negative I, 1, 1. And then 0, negative I, negative 1. And then finally 0, 1, negative I. So I'm going to have zeros on the right-hand side. And I want to do a little bit of row reduction here. And so I'm going to get, let's see, negative I, 1, 1, 0, negative I, negative 1. And then I'm going to notice that if I multiply the bottom row by I can add the rows together and get 0, 0, 0. So I do get a row of zeros. The right-hand side is still just 0, 0, 0. Okay, so I need to find my next eigenvector. The way I'm going to do that is I'm going to put a 1 on the bottom, okay? That means that if I have a 1 on the bottom, that in order for the second equation to work out, that I'm going to need to have an I here. So just so that you see that, maybe I'll put it in red there. For the second equation, I'll have negative I times I minus 1 times 1, which is, of course, going to be 0. So that works out. And then for the third equation, I'm going to put a 1 minus I on top, for the top equation. And that is simply because, again, if I'm looking at the top one, I'm going to have a 1 minus I times negative I, and then I'm going to have plus I plus 1, and that will give me, yes, 0. Okay, so you can solve these yourself, but I'm going to take a little bit of a shortcut and just solve those right there. Okay, so now what that tells me is that I need to write down the solution, y2. I need to write it down in complex form, and that solution is going to be e to the 1 minus I times t. And, it's e to the 1 plus I times t. And that's going to get multiplied by my eigenvector, 1 minus I1. So that becomes e to the t, and then the e to the it becomes a cosine t plus I sine t. And then we're going to multiply that by my eigenvector, 1 minus I1. And then we want to split that into real and imaginary parts. So each one of them is going to have an e to the t. So we're going to have e to the t times something plus I e to the t times something else. And we just want to split these into real and imaginary parts. So I see that the cosine t is going to get multiplied by 1. So I'm going to get a cosine t there. And I'm going to get that the I sine t is going to get multiplied by minus I. So that's going to give me a plus sine t. Then the I sine t would get multiplied by the I in the second row. So that's going to give me a minus sine t. And then the cosine t gets multiplied by the 1 in the third row. So that's the real part. Now the imaginary part, factoring out the i's, is going to be cosine t minus or times a minus I. So that's going to be a negative cosine t. We're going to have that I sine t gets multiplied by 1. So that's plus sine t. Cosine t gets multiplied by the I in the second row. So that gives me a cosine t. And then finally, for the third row, I have an I sine t times 1. So that gives me a sine t. And so we will call this one u of t, and we will call this one v of t, so plus, say, I times v of t. And those will be my other two linearly independent solutions. So y of t in this case is actually going to equal, so e to the 1t times the eigenvector 1, 0, 0, plus, so that's going to get multiplied by a c1. And then c2 e to the t times u, so that's cosine t plus sine t, negative sine t, and cosine t. And then finally plus c3 e to the t times negative cosine t plus sine t, cosine t, sine t. So as you can see, getting the general solution is a very involved problem. Okay, we now need the initial condition. So what is y of 0? So y of 0 in this case is going to be a matrix. I'm going to form a matrix using essentially these as my columns when I plugged in 0. So the first column is going to be 1, 0, 0. The next column is going to be 1. The sign of 0 is 0, and then 1. And then my third column is going to be negative 1, because the negative cosine of 0. And then I'm going to get a 1, and then the sign of 0 is 0. So that gets multiplied by C1, C2, and C3, and that's supposed to equal 0, 1, 0. Now, you can actually kind of read off the solutions pretty easily without doing some row reductions here. You can see from the second row that we get that C3 is equal to 1. We can see from the third row that C2 is equal to 0. And so when you combine those two things, then you can see that we have C1 plus C2, which is 0, minus C3 is equal to 0. So essentially C1 and C3 have to be the same. So C1 must be 1. And so y of t, if we combine all of these things, is going to be e to the t times, well, I get 1 of the vector 1, 0, 0, and then 1 of the solution negative cosine t plus sine t, cosine t, sine t. And so that solves now the initial value problem. It's important to note that you might have gotten a different general solution than I did based on how you chose your eigenvector. But once you plug in the initial condition, then you should get the same solution that I got. You'll get different constants maybe for C1, C2, and C3, but your final solution should be the same.